All right, and then we have strong bases. So a strong base is actually any group 1 or 2 metal with hydroxide. So for example, we can have lithium hydroxide, right? Because lithium's in group 1. We can have calcium hydroxide, calcium's in group 2, etc., right? Potassium hydroxide, sodium hydroxide, magnesium hydroxide. If it is not a group 1 or group 2 metal, so even if it's something like aluminum hydroxide or iron 2 hydroxide, those are not considered to be strong. So meaning they are not 100% dissociated, right? So as soon as we get into the realm of not being 100% dissociated or ionized, now we're dealing with something weak. That means you have equilibrium. So we're not dealing with that today. Like, I want you to know the concept of like what makes something strong or weak, depending on the association, the dissociation or ionization percentage, right? So remember, 99 plus, that means there's no equilibrium. Okay. After this lesson, when we go further into chapter 8, we will talk about what happens when we do have equilibrium, which means weak acids and bases. But for today, we're kind of just going over theory and strong acid base. Okay, so our next example we have here, or our first one, is what is the hydronium concentration in a solution of a 0.025 mole per liter solution of NaOH at 25 degrees Celsius? Okay, so we're told the concentration of sodium hydroxide, and we're also told it's basically at SATP temperature, which is going to come in handy. So it doesn't outright tell us what the hydroxide concentration is, but we're going to use our molar ratios to help us, because remember that this is a strong base, so it's not equilibrium. We are assuming 100% of that sodium hydroxide has become our product. So we have 0.025 hydroxide because we have 0.025 sodium hydroxide. So now we basically have hydroxide, and to find hydronium, because this is at SATP, we can use our KW standard. So meaning in any solution at SATP, the hydronium times our hydroxide should equal 1.0 times 10 to the negative 14. So we have our OH, and we're solving for hydronium. We simply rearrange that, and we get 4.0 times 10 to the negative 13 moles per liter. And of course, it's 2 significant digits. Okay, so for the next example, what is the pH of a 0.002 mole per liter nitric acid solution? So again, this is nitric acid. So because this is a strong acid, 100% of that is becoming product, which means hydrogen. And we know that hydrogen, whenever it's in water, is really hydronium. So this ultimately is our hydronium concentration. So actually we can find pH pretty easily. We just do the negative log of that. So in this case, it's down to 1 significant digit because of the 0.002. So again, the difficult part of this is going to be once you start learning weak acids and bases, you have to recognize, oh hey, this is a strong acid, so you know that this is not in equilibrium. So it's just something to always look out for when you're reading the acid or base type to think about. Alright, so then we have, not fully in the screen here, let me see if I can change that. No, it's okay. I'll shift it over. Okay, so example 3, and also you have this in your notes anyways. Example 3, calculate the pH and pOH of a solution prepared by dissolving 4.3 grams of barium hydroxide in water to form 1.5 liters of solution. Okay, so we have barium hydroxide. So first of all, we're recognizing that it's a strong base. It's a group 2 with hydroxide. We have the mass. We have the volume, and we want to know pH and pOH. So essentially, before we can do pH or pOH, we need to get the concentration. So concentration is equal to moles per liter. We have the volume, but we need to find moles first. So this first step, we're doing mass over the molar mass, right? So barium hydroxide, we have 1 Ba, so take a look, it's a crisscross rule, 2 oxygen and 2 hydrogen, mass over molar mass. We now have enough information to solve for C. So concentration of barium hydroxide is moles per over volume. It's already in liters. Okay, so here is the part where you have to be wary of. So remember how the other examples, our ion was in a 1-to-1 ratio with the original compound. So in this particular example, we have barium hydroxide, and there's 2 OHs for every 1 barium hydroxide. So what that means is this calculated concentration is for the entire compound. But to find, let's say, POH, which means we need the hydroxide concentration, we would have to do double that. So see how I have here, we have 2 OHs, so essentially it's a 2-to-1 ratio. So we have to double the concentration, and that kind of makes sense. For every 1 barium hydroxide, there is twice as many hydroxide ions being produced. So the concentration should be doubled. So now that we have that information, we do negative log of the OH to get the POH. And then, of course, to get the pH, we do 14 minus the POH. So we get 12, 1.5 and 12 after significant digits. So the work for today's lesson is really all about strong acid, strong base, with, of course, the theory behind Bronsted-Lowry's acid-base definitions, right? We're looking at conjugate acid-base pairings. It's very important that you make sure you practice that, because our next topic, when we go into weak acid-base equilibrium, you're going to see that conjugates become very important for determining equilibrium concentrations and pH. Okay, have a good day. Thank you.